Dominik KWIETNIAK from Kraków, and he will talk about the Toolbox. Thank you.
Thank you very much, Katrin, for the introduction, and thank you very much for all the organizers for their work. I've been there a little bit, so I know it's not so easy. Regarding the nice announcements, so you know, usually those courses are run by two persons crews, so they are 2 lecturers for 1 mini course. I'm super happy that I got this opportunity to speak all by myself, and because of that, so that it is maybe not visible, but if you look more carefully into your programs, I'm still speaking as 2 people, because on Wednesday there will be Dominik KWIETNIAK from the Federal University of Rio de Janeiro. Today I'm from Kraków, so this is still a mini course run by 2 persons. So, okay, ask him for why it happened. I don't know. So, guys, my goal here is to tell you how to prove that classification is impossible. So basically, the whole idea is to introduce and explain certain philosophy which is behind proving that something is impossible. So I will get to that back later, but the important part is that whenever you say that something is impossible in mathematics, you always have to explain in which sense. Because this is, without that, something is possible, and say using axiom of choice, a lot of things are possible. But hard to see maybe, but still possible. So I will tell you about that later, but let me state it from the very beginning that I have my very particular sense in which we will be talking about things which are impossible. So this is not algorithmic impossibility, because algorithmic impossibility is usually defined as something that you have a task for which you can build a Turing machine which has a finite input, and in finitely many steps it returns the answer. This is a very strong notion of computability, and we are mathematicians. We are made for more abstract stuff, so we leave it to computer scientists how to deal with this kind of stuff, and we are really after countable contability, which means that we are really going after doing something into countably many steps, so you can think of it inductively, but we need a little bit more sophisticated version of induction, which is an induction over countable ordinals. But okay, let's leave it for a moment. So I have, well, with the other guy, we have 3 lectures, and those lectures are, well, I didn't know that those will be titles of the lectures. I thought that I'm just giving an outline what will happen in this stuff. So this will be, those lectures are concentrated on the toolbox, aka rules of the game, right? Because always solving mathematical problems is a little bit like playing a game. So therefore the second part, I will introduce quite a few stuff. And I know that they are very good specialists for whom this will be boring, but I also believe that majority of people doesn't know this stuff by heart, at least. So I will introduce the rules of the game, and the 2 other lectures for those brave souls which stay with this mini course for the rest of the week. Maybe I will start bringing cookies like Lorenzo, or try to buy your attention in other ways. So those are the scoreboard. So this will be kind of a presentation on overview what we know using the language which we are going to build today. And finally, for really the bravest, there will be some action. So actually some more insight into the proofs, how you can play this game in order to prove some impossibility theorems. Okay, so what usually in dynamical systems, we have one problem, which is like that we, in comparisons with, say, I don't know, theory of groups, we don't have like a very finite list of axioms with which we work. We have some list of axioms, but then our whole field decomposes into different parts in which we study different families of dynamical systems, because it is very hard to use find general rules and general axioms which would say something non-trivial about interesting examples. So for many of those families of dynamical systems, we have, you can find open questions. And those open questions, the most general one starts with the order which tells you to classify. Classify, blah, blah, blah. And this blah, blah, blah is now your favorite family of dynamical systems. And I think that it is fair to say that the perfect answer is the answer which was known which was provided by Poincaré. So imagine that we finish this problem with the classify minimal homeomorphisms of the circle. Right? Actually, so we take, say, if we want to be more specific, okay, let us think about orientation-preserving homeomorphisms of the circle. So every orbit is dense. So then we know that there is a fantastic tool which is the rotation number. And the rotation number, you can think of it as like real number modulo the integers, and rotation number tells you all. Two orientation-preserving minimal homeomorphisms of the circle are topologically conjugated, even only if they have the same rotation number. So you have a perfect classification, but not only you have a perfect classification, but moreover, you have a complete invariant. You have a function, and this function is not a function, but a nice function. It is, if you introduce the topology of uniform convergence for minimal homeomorphisms of the circle, then rotation number is a continuous function. So I said this is a continuous function, and it nicely divides the space of minimal homeomorphisms into equivalence classes up to the topological conjugacy. So this is like a positive example. Another well-known example, which you can probably guess right now, which is a little bit less obvious, is the Bernoulli measure-preserving systems. So that's, well, Ornstein or Ornstein-Sinai theorem, which tells you that two Bernoulli measure-preserving systems are isomorphic, even only if they have the same entropy. So let us agree that if I don't define something, then either I expect, then this means that I really will not need this definition later. So I hope that even if you don't know what some terms here means that you can have some feeling what the theorem says. So we have isomorphism in the sense of the measure-preserving systems. Here, the problem is that in comparison with the previous classification problem, that you can complain a little bit that, okay, so what? Entropy is a function, but is it a nice function? Unfortunately, when you look at the most natural topology for those measure-preserving automorphisms, the Bernoulli systems, the entropy is usually not a continuous function, but at least you can still prove that that this function is computable using inherently countable techniques, because that's a Borel function still. And you can still end out the space of our Bernoulli measure-preserving systems with a topology which makes it a sufficiently nice topological space so that you can talk about Borelness, and this all becomes meaningful result. So this is another positive example of a successful classification using some countable techniques. Okay. And if I was going to talk about the positive examples only, that I'm close to my mini course. Because not so many natural or very well-studied examples are known. And so now we turn our question a little bit. So instead of, say, classify, then we say classify or prove that it is impossible. So exactly for this moment that you would like to prove that something is impossible, then you really need to introduce some framework. It is like the same story with the proof of the impossibility of proving the parallel postulate using the first 4 axioms from the Euclidean geometry. You need to talk about, yes? I'm going there. It's like I said something and I said be patient. So please a little bit, and this is why you shouldn't be late to lectures. Okay. Now prove that it is impossible. So in order to prove that proving a parallel postulate is impossible, you have to a little bit go outside pure framework of geometry. You have to start about axiomatic theorems and independence of axioms, and only when you specify what do you mean by having a model, and the existence of a model proves impossibility of getting one axiom derived from the others, you have your impossibility. And you have a precise sense in what does it mean that it is impossible. So here, if we want to prove that something is impossible, we need to go into the direction of Borelness. So inheritably countable more or less means the same as Borel techniques. So now I have to excuse all of you who know all this Borel stuff by heart, but I feel really that I should do a little summary of those results and introduce some notions. So let us go into the Borel world for a moment. If X is a topological space, then there is a family of open sets and this family of open sets for a given topological space allows you to generate the smallest sigma algebra containing of all open sets. So this is so-called Borel sigma algebra. Unfortunately, general topological spaces are a little bit wild, and the notion of being Borel is also a little wild in the general topological spaces. For example, you may have situations that with the product sigma algebra, the diagonal is not Borel. You don't want such crazy examples like that. You want to exclude crazy examples like that. So what is the solution then? Okay, is to, well, this is the moment in which I always feel I don't know, I should sign an anthem, or I don't know, it's because it's, you need to assume that your space is Polish. So what is a Polish space? A topological space is Polish. So, I did it because I could have red and white definitions. Okay, let's go. The space is Polish if it is separable, so there exists a countable dense subset and completely metrizable topological space. So we have a space, and this topology is such that if we be a little bit more careful, then we are able to find a dense, countable dense subset of the space, and we are able to find a metric such that this metric gives us the topology and is complete in the usual sense that every Cauchy sequence converges. So in fact, mathematicians very well, in most fields of mathematics, most of mathematicians never leave Polish spaces. We always live and work in Polish spaces. This is not a claim of any kind of dominance, but a simple fact. And what? We live in Polish spaces because Polish spaces are abundant. So every compact metric space is Polish. So we have this. A very good example of a Polish metric space is the set of irrational numbers, because this illustrates one fact, that not necessarily the natural metric for our space is the complete one, because we take the irrational numbers with the topology inherited from the real line. If we take the usual metric, which we inherited from the real line, this is not complete. But the point is that there is a method of, well, nice exercise if you haven't seen that, what defines such a metric, right? But this is also Polish space. Now, if G is any countable set, and we introduce the discrete topology, then it will be also a Polish space, because due to a very trivial reasons that any Cauchy sequence has to be eventually fixed, which means that it has to converge. And the dense set, countable dense set is the space itself, so this is immediately Polish. A little bit less known fact is that if you look at the space of ergodic, you take your compact dynamical system given by action of a continuous map on the compact metric space, and then you take the set of T-invariant ergodic measures. Then this is always a Polish space with the natural weak star topology. On that, what can be really more surprising, that every Polish metric space has to appear as topologically as the set of invariant measures for some topological dynamical system. So we already know them all. Sorry?
So every kind of space
Yeah, so if you know that that your space is homeomorphic with the set of ergodic invariant measures for some compact topological dynamical system, then you know that it is Polish. And in the other direction, if you take your favorite compact, meaning that continuous map acting on from a compact metric space to itself, then we know that if you take any Polish metric space, then you can find a metric space, a continuous map from this metric to itself, such that the set of invariant measures for that system will be your favorite Polish space. So in the topological sense, right? Because, okay, it is very bad to imagine that the topology of this space is enough to determine the whole simplex. This is not true. So this is true only if this is compact. If it is not compact, but this is irrelevant for that. This might be interesting information to know but it is does not belong to this course. So let's stop here. So we have those examples, and I'm checking if I am not forgetting about something. Okay, so of course, all these, if I take X compact and I take the set of all continuous functions on my compact metric space with the uniform topology, that's Polish. If I take the Lebesgue measure on the interval and the set of all equivalence classes of the functions integrable in the power p, then for p greater or equal than 1, this is Polish metric space. If I take okay, this is maybe a little bit less common space, because, okay, you may think that, okay, what I wanted to show, that Polish spaces are not necessarily vector spaces, because if you look only at those examples, you may think that, okay, those are mostly vector spaces. But if you take the set of all non-empty compact subset of R to the n for some n, and if you take the Hausdorff metric, that will be again the Polish a Polish space. So a lot of Polish spaces, and it is harder to find a non-Polish space, non-trivial non-Polish space than not to find. It's like, okay, if I go to the extreme examples, then I take the topological product of 0, 1 to the R. This is compact, not metrizable space, and it is not Polish there. But it's, well, who needs that space after all? It's not as much as interesting. So, and of course, another example is if I take integers with the topology inherited from R, and then how can you see that this is a non-Polish space? Because, okay, this is not enough to say that, okay, with the usual metric, this is non-complete. Rationals. Thank you very much. And this is also why people in the first row should be very active. They help the speaker. So, rationals. Rationals with the usual topology, I'm sorry. This is not a Polish space, but, okay, if you take the usual metric, you may say, okay, maybe with some different metric, it is, but a nice fact about Polish spaces is that they are really, if they have if they are dense in themselves, then they have to be uncountable. So if no point of the space is or 1 point. So if you have a space with more than 1 point and no point is isolated, then necessarily the cardinality of the space has to be uncountable. So this is how you can justify that rationals they cannot be Polish because they are countable and no point is isolated, and it is not, well, so they cannot be Polish. So let me repeat. Polish spaces are nice. So for doing Borel stuff, Polish spaces are nice. So if you take Polish space, if you take the family of all open sets in that space, then if you generate the sigma algebra out of this, you get a nice family. And if you really take an uncountable Polish space, then the Borel sigma algebras, in the sense of isomorphism of Borel sigma algebras, they are all the same. They are all the same. The structure looks the same. And now let us go back a little bit. Why Borel is related to inherently countable techniques. So in order to produce all Borel spaces, you have to keep adding sets, because in the usual, in the classical Borel, in a Polish metric space, you start with all open sets, and then this family is closed with respect to countable unions, but if you want to generate the sigma algebra, it has to be also closed with respect to countable intersections. So, okay, you start intersecting countable families of open sets, and they are G delta, so those sets are called G delta, and there are known examples of a G delta sets which are not open. So you already have to add. On the other hand, every sigma algebra is closed with respect to taking complements, and if you want to have a sigma algebra generated by open sets, you need to take complements. So you automatically are adding all closed sets, but not all closed sets are open. Usually, if the space is connected, that there are only two open and closed subset, which is empty set and the whole space. So you keep adding. And then you have, okay, you have a family of F sigma sets. So you added some sets which are neither open nor closed, but they are countable unions of closed sets, and you added G delta sets, which are countable intersections of open sets. Is that the end? Not necessarily, because now you can take countable unions of G delta sets. Unfortunately, not every countable union of G delta set is, again, G delta. So you are adding. So basically, using those three basic operations, taking countable union, taking countable intersection, and taking complement, you are climbing up the ladder. You are keep adding your sets. Okay? And are you done after doing infinitely many steps? No, again, not necessarily, because you may take some sequence of sets you generated along your construction, and I don't know, sum them up, and you are not guaranteed that you will see some again. Quite on contrary, you are guaranteed that you will see some new sets again. But this is like going up the countable ordinals ladder, and it's a theorem you can prove for the set theory course. Not super complicated. Is that okay? If you perform all countable steps in the sense of countable ordinals, then you will then produce our Borel sets. So for every Borel set, there will be some countable ordinal, and there will be some procedure of producing this Borel set from basic open sets by taking complements, unions. Okay, if you allow complements, then you may forget about intersections by the Morgan laws, so you can take countable unions and complements, and you will generate it. So then, what does it mean? That for every Borel set in a Polish space, there exists a countable procedure of asking questions to decide whether an element is in this set. And those are yes/no questions. You ask, you pick okay, the space is separable, so there is a countable base for a topology. So that's countably many open sets. And then for each of these open sets, and so we have the space, very little Polish space, and we have our Borel set, and we have a guy in our space, and it is somewhere there, and we want to know, are you Mr. by chance in B? And we can start asking questions, like in this, 21 questions game. Are you in B1? Yes, no. Are you in B2? Yes, no. Are you in B, and etc. So that's countably many questions, and once we hear the answers, the structure of the Borel sets give us a way of combining those questions in a countably many steps given by your countable ordinal to provide you the answer. I know that it might be, if you don't have a good experience maybe or some experience with countable ordinals, this might sound like blah, 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 whatever. But I hope you can believe in that it is not necessarily really to have a good mathematical understanding of this statement. This is more like a philosophical explanation why taking this why Borelness means inheritably yes.
So you're saying countable set of questions you can always answer yes or no, but the question.
Yes, but after I also have some tree of combining those questions into intermediate answers, right? Because
in the end, you are guaranteed that you can always. This is for any Borel set B and for any point X in X.
Yeah. Yes. So for any Borel, there's this countable procedure using countable information. So you have a sequence of yes or no answers, and then there's this countable procedure. So this is like the algorithm running on infinite induction, but not really, not in a finite induction, but by transfinite induction, but still countable, right? So there is no need to appeal to very strange objects like the axiom of choice, which will give you answer out of nowhere. You don't know. So what is maybe interesting to also remember that with these Polish metric spaces, we can do a lot of analysis in topology without actually using the full force of the axiom of choice. If you are more into basics of mathematics and you are asking what kind of axioms you need to do the stuff, if you want to stay inside Polish spaces, then you don't really need the strange axiom of choice. You really need an axiom of dependent choices. So after countably many choices, you need a method which guarantees then you can do the next one. And then you do everything with the inductive procedures. A lot of proofs goes by induction, transfinite induction. So this is like a much more, in a sense, much more concrete theory than the general mathematics. Okay, but this is really like philosophical one. So now we have Borelness. So this, what is a consequence for? We went long way from the game, but now what is a consequence for this classification problem? The consequence of the classification problem is, again, to be honest, I find most of the mathematical jokes very cheesy, and this is one of them. So, what is the how you teach a mathematician to boil water, right? So you ask him first to fill the, what's the name for the what? So, or kettle, thank you. I prefer kettle. So you fill the kettle, put it on fire, and the water boils, you have your water boils. What if you start with the filled already kettle with water? It's simple, you throw water away and then you reduce to the previous step. And, but this is what we will do, right? So this is really the very basic idea of reductions, because yeah, how to boil water. So you can always say the following. To solve problem P, reduce it to P prime, which is a problem that you can solve. Right? To solve problem P, reduce it to the problem P prime that you can solve, like with boiling water, and but it has a contrapositive statement. If to prove P prime is impossible to solve, find another problem P that you know it is impossible and prove P reduces to P prime. So in this context, what does the reduction mean? It means that you can take one problem and somehow do the recoding of this problem into maybe some completely other domain. And in some sense, if you, let us do this into the following. So we have, an abstract classification problem consists of two objects, a set X and an equivalence relation E on X. So we look at the equivalence relations as subset of the X times X, right? The usual stuff. So an abstract classification problem usually reduces to this situation. We have some space, and on that space, we have an equivalence relation saying exactly the two objects we are interested in are equivalent, isomorphic, whatever, even only if they are in the same equivalence class. Here, I cheat a little bit because in many occasions in mathematics, it happens that the collection of all objects we consider is not really a set. It's a proper class, whatever. But even in those situations, usually, we can always guarantee that we will find a single decent space in which every equivalence class will have its representative. So we can forget about that and reduce ourselves to the setting in which we are really sitting on a set. So now let us assume we have another a y and maybe let's write y e x, x e x, y e y. So those are two pairs and corresponding equivalence relations. So what would be a good reduction? So a function, so definition, a function phi going from x to y is a reduction of x ex to y ey if we have the following for every elements x1, x2 in X, we have that x1 is in the relation E with x2, even only if f of x1 is in the relation f ey with f of x2, right? So this is exactly what do you mean by the reduction. We have one problem and another problem, classification problem, and we can translate one problem into another by a special function which has this property that if I take two objects in the space I'm interested in, and in order to decide if they are equivalent, I translate them both to the space in which I can decide, and I decide there about the images, and the property of the reduction tells me that, okay, if I decided in Y, yes or no, that the same answer holds in X. So this is the first part, right? And the other is really like reasoning by contradiction, right? So assume I have a problem, I have a reduction of this problem to problem on Y, and I know that the problem regarding solving this X is impossible, and I have this reduction, so it means that the problem on Y has to be also impossible to solve, because otherwise, using the reduction and the solution of the problem on this space, I would solve the problem I know is impossible to solve. So now, no, we don't have to. We just have to. We just have to have a faithful coding, such that the guys which are related stay related, and the mapping does not create any additional relations than they were in the beginning. What? Okay. So, and of course, the setting in which we will work is really that we take Polish spaces and reduction of and reductions given by Borel functions. Because again, being Borel is something which means that you can compute it using countably many steps and having countable information. And this means that those Borel functions, then they are substitute of a decent algorithm of translating one problem into another problem. And then, yeah, you have you have your reductions. So, okay. So, okay, time. So right now we know what we want to do. We really want to. Okay. Let me keep introducing some notions. So, if the function phi, as in the definition of the reduction as above, is Borel, and let us also make a standing assumption that X, Y are Polish spaces. So if phi is Borel, then we write like Ex smaller or equal in the Borel sense to Ey. Which means that in the Borel sense, the relation on X, equivalence relation on X, is at most as complicated as the relation Ey on Y. Maybe it is simpler, maybe not. And now we have, we write that Ex is in the Borel sense, Borel equivalent to Ey, even only if we have, of course, the inequalities in both directions. So one is irreducible to the other, and the second one is reducible to the first one. So this is the reduction. This is the reduction from the previous definition. That a function.
But when does phi appear an error in the definition of f later? Phi in the definition.
I'm sorry. What? Phi?
Oh, that's phi.
That's phi, of course. Yes. I'm sorry. Sorry. No. This is my. I concentrate so much what I'm going to say that I write rubbish. This is very likely, so don't hesitate to interrupt me. So, no. That's the point. They don't need to. The reduction is Borel. This is like our way of recoding one problem into another is Borel. But those guys, no. They need not to. They will appear some guys which are not Borel. No. So of course, that's also a very good question. It is the relations for which the set Ex is Borel when you endo the product space with the product of Borel sigma algebras, they are much nicer. Because the relation being Borel means that, okay, at least you have really this countable set of questions which may be very complicated you can ask in order to resolve the stuff. And if the relation is not Borel, that not only invariants are impossible, even this very vague algorithm is impossible to provide. So yeah, those sets are much more complicated. Okay, Borel, yeah. So now, what is then the game? What is the game? The game is really to say the following. Okay, we now have a way of comparing any two equivalence relations on the Borel spaces. And this is a very old idea humanity had a long time ago, is to simply, okay, I need to remove something, so let's start removing. So simply, it's like you use measuring stick. You take a stick and you claim that this is one meter, and since that moment, it's your unit. And this is 1 meter. So it would be great if the order we had was, well, very nice linear, right? And then we could try to introduce scale on that measuring stick, and given any problem, we would like to measure its complexity by comparing it with the known marks. Okay? It almost works. Almost means that this is only a partial order on the equivalence classes, because, first you have to somehow identify the relations. Okay, you have to forget about that partial orders can be also defined on proper classes, whatever. But, so this is a partial order on the equivalence classes, and it is really partial. So they are guys which are incomparable. The picture is, it is at least as complicated that you can really take the copy of the set of your natural numbers, and then you can order this by the relation of containment, and you can embed this tree of relation into the relations between Polish equivalence relations. So this is at least, this is a mess. But this is also why it is nice, because the answers are not so easy. You have many possibilities, and you have some scale. And then in order to find the proper place of your guy in the, so first of all, there are still some open questions about this picture here. Well, much more complicated picture, which I hope I will be able to draw you on Wednesday. So on Wednesday we will be really feeling this picture, but let us talk about some simple relations. So from now on, n equivalence relation means n equivalence relation on a Polish space. E, we say that n equivalence relation E is smooth if E is Borel reducible to the identity on the reals. What does it mean? That this is really the simplest possible equivalence relation you can imagine. It's equality of two real numbers. And this is maybe one good example to see the illustration that actually identity on the reals is Borel equivalent to identity on any other uncountable Borel space. So the reals is any other space is good. And so let us look, what does it mean, what I wrote? It means that you can find a Borel invariant for your equivalence relation. This means that for your equivalence relation, there exists a Borel function from your space to reals with this property that two objects are equivalent even only if the function associates to them equal stuff. So smooth relations are in this sense, the examples of the smooth relations are those examples I started my talk. And this fact that the entropy function is not continuous by Borel also explains why you need to here talk about Borel reductions. So Borel reductions we need, and smooth relations are the easiest. And if the relation is not smooth, then in this sense, we already know one very important thing, that finding a set of Borel invariants, so functions which provide you even, well, because like a space of sequences of real numbers is still Polish. So we cannot hope even for a sequence of Borel invariants providing us the classification. Not possible, simply. So those are all already hard. But this is just the bottom of the scale. So one can prove the following. There exists the next relation. So the bottom of the scale has this nice stuff that we know what is the smallest element here, and in some sense we also know the next one. So it is E0. So E0 is you take the relation. So two sequences, xi and yi, where xi I from say 1 to infinity, yi from I equal 1 to infinity are elements of the space 0, 0, 1 sequences indexed by the positive integers. So those two guys are in this E0 relation, even only if it was Aaron who talked about this. I don't remember. It was the equivalence relation he used, but in the other direction. So we have that there exists n0 such that for every I greater or equal than n0, xi is equal yi. So this is an equivalence relation if when two 0, 1 sequences are related, even only if they are eventually equal. And, well, you can try to prove that this is already the very simple example of something which is not smooth. So this, for this relation, you already cannot provide finite invariance. So okay, I have a plan to give you a dynamical system proof which appears in this theory of equivalence relations, but I don't have time for that. So I'm sorry, maybe I will be able to provide this proof for the notes, because it's really like how you can use a notion of topological transitivity to prove that some equivalence relations are not smooth. Basically, a smooth equivalence relation, because if we have a countable, so you can imagine now, if you have a countable equivalence relation, which means that each class is countable. Each equivalence class is countable. Like here, it's an example of a countable equivalence relation. So we can think about the equivalence class in the space X almost like an orbit of some action. Not necessarily Z action, but some countable group action. And the question is now that if there, for this guy, there appears a non-trivial recurrence, meaning that there will be one guy in one equivalence class which will be the limit point of other points from the same equivalence class, then it cannot be smooth. So this is, instead of a proof, a story. And thank you very much for your attention.
Any further questions?
I was so curious about if there is, if you can mention some classification problem that is impossible.
Sorry?
If you can mention some example of classification that is impossible.
So resolving this is impossible using any Borel invariant. This is a simple equivalence relation, and you have a Borel procedure for doing that, but you don't have, yeah. And if you want to get the really, I will get to that, but among all analytic equivalence relations, isomorphism of Banach spaces is a completely bad, undecidable in any countable sense problem. So if you want you need to introduce a notion of the, I think you need for that the universal Banach space, so such a Banach space that every other Banach space embeds into that, and some kind of structure on those points, but you can prove that actually you cannot decide whether two Banach spaces are isomorphic in any reasonable way, than just saying, okay, they are isomorphic, or having luck with finding actual isomorphisms. There is no procedure in the inherently countable sense.
Okay.
So a smooth action is really, E is not, as complicated as the identity. So identity is a very simple equivalence relation. So you take two objects, and if they are equal, good. If they are not, bad. And if you can reduce to this kind of question, it means that you have a single function which is an invariant, which is like entropy or temperature. You measure temperature, and you know if you are in the equivalence class of healthy people or sick people, right? It's like, I don't know, 37, say. That's the difference.
Okay. So let's thank Dominik again.